My name is Nate Gemelke. I'm one of the co-founders of QuEra's and the Chief Technology Strategist. QuEra's founding team was very heavy on the science. So we had a very strong and biased viewpoint about not just where quantum computing was at when we started the company, but also what quantum computing meant in the first place. And for a lot of us, we've had long careers that stretch almost all the way back to the early days of thinking about quantum computing. And if you go all the way back to that, one of the people that led the charge of thinking about why quantum computing would be interesting in the first place was Richard Feynman. He gave a very famous lecture on this, and towards the end of that lecture, one of the things that he said is that you could imagine a quantum computer would have to be, and then he described what is basically what we make now, just single spins that interact with each other or lined up in special ways and then kind of processed in a way that would make a computing algorithm. But the reason that he said it was actually what he had in mind were quantum systems themselves, and the fact that they do things that classical systems don't do efficiently, and kind of turned the problem back on itself. And he said, well, quantum systems would be a great way of studying quantum systems. And what he really had in mind was quantum simulation. Most of the founding team had been doing quantum simulations with neutral atoms for a very long time, trying to apply how those quantum systems might give us information about, say, how superconductivity works, which is its own quantum system. That you're basically training one quantum system on elucidating the nature of another one. That quantum simulation in some ways is much harder to do than quantum computation, in some ways is much easier to do than quantum computation. And neutral atoms really had the lead on quantum simulation, while other parts of the world were waking up and trying to do quantum computation at a very small scale. So we knew we would be good at this, but we had been basically focused on the natural physics problems for a very long time. And many of us kind of woke up one day and said, I'd like to be doing many more of these quantum simulations, much better, much faster. And that really does start to get into the aspects of programmability and the difference between a quantum computer and a quantum simulation. And we had advanced the neutral atom hardware sufficiently by that point that it really made sense to start calling it computation, start designing the systems differently, confront some of the harder challenges of programmability. And once we started doing it, it was addictive. We got good at getting programmability into it, and we were actually computing before we really realized that we probably will be. Kind of connecting back to the theme of simulation and computation, there is a way of thinking about these things on two axes of kind of scale and programmability. And you might think of quantum simulators as being very special purpose and therefore not as programmable, but high scale systems. And in that sense, we took a path that in the very early days of QuEra's, was following a kind of lower programmability, higher scale pathway. But then we had some discoveries. We discovered how to do arbitrary gates and create architectures that had all-to-all connectivity. And these are really key steps to enabling universal computation. And the minute we realized how to do those things, and we were the first to get to that point, we became experts overnight in the programmability axis. And so we kind of switched gears at that point. We really started to figure out how do you implement error correction, which is a necessary step to be able to build a useful quantum computer. It was surprising how rapidly we were able to confront those challenges. Once we were able to do that at kind of medium scale, we started to think about how to scale it up. We figured out how to confront the key challenge to scaling up, which is how do you replace the atoms that are lost continuously in a calculation? We thought that would take us 2 years. It took us 6 months to solve that problem. So once we had gotten through those challenges, it really opens the door. And now the key step is really how do we scale that further? To some extent, scaling, just making a neutral atom system larger, there are some aspects of that that are trivial and there's some that are non-trivial. the trivial ones, we've sat down recently and we thought about that long-term pathway. The engineering challenges are solvable engineering challenges, where there are non-trivial things that are left to do. And some of this is engineering, some of it is more fundamental knowledge that has to be created and gained, is thinking about how applications, algorithms, and error correction really intersect as you scale, and how you efficiently manage your resources in order to implement a particular challenge. A lot of times we talk about this as moving the goalposts. If I want to perform a useful calculation on, saying, factoring integers, or thinking about the electronic ground structure of a molecule, or designing a material, something like that, you really do need to think about how to use the resources efficiently while you're getting all the benefits of error correction. And there are smarter and less smart ways of doing that. The smarter ones move the goalposts in terms of how many qubits do I need, how many gates do I need, closer to where the hardware is at now. So we've become experts in both games at making the hardware better and more performative, but also moving the goalposts sooner by thinking about how do applications work, how do they solve real world problems, and how do we minimize the resources necessary to do that.